In this section, we're going to continue looking at discrete probability distributions, but we're going to focus on one specific kind of discrete probability distribution called the binomial distribution, and it's one that we use a lot in statistics. So first of all, what are binomial experiments? One thing you want to note is bi means two. So we're going to say that with binomial experiments, there are two main outcomes. Instead of having 5 outcomes or 8 outcomes like we've seen in other examples, particularly in the last chapter, you're going to have just 2 outcomes. So there are many types of probability experiments for which the results of each trial can be reduced to 2 outcomes, either a success or a failure. For instance, when a basketball player attempts a free throw, he or she either makes the basket or does not. So we could consider a success being that they made the basket and a failure being that they did not make the basket. Probability experiments such as these are called binomial experiments. To be more specific, a binomial experiment is a probability experiment that satisfies these 4 conditions. The experiment has a fixed number of trials, where each trial is independent of other trials. There are only 2 possible outcomes, and we classify them as success or failure. The probability of a success is the same for each trial. So that probability is the same. It's not changing because we have independent trials. And then the random variable x counts the number of successful trials. So what x represents here is the number of successes. Now for some notation, we're going to use n to represent the number of trials. So however many times we're repeating this, this idea. So if we're going back to the free throw example, we could maybe have that basketball player throw 10 free throws in a row. So if he threw or she threw 10 free throws in a row, we could have up to 10 successes, right? We could have x is 0 successes, 1, 2, 3, 4, all the way up through 10, depending on how many shots he makes or she makes. P is the probability of a success of a single trial. Q is the probability of a failure. So what we can do is we can use the complement here to find the probability, because remember, those 2 things will add up to 1. So if I know the probability of a success, then I can find the probability of a failure by subtracting it with 1 to get the complement. And x is the random variable, and again, it represents the count of successes in n trials. So for instance, 0 means that there are 0 successes, there's 1 success, there's 2 successes, there's 3 successes, and so on. Now, one thing I do want to note is a success does not have to be positive. We can define it in any way we want as long as we're clear about what we're calling a success. So for instance, let's say we were researching identity theft. We may define a success to be a person who was the victim of identity theft. So again, the word success in statistics here doesn't have to be a positive outcome. It's just really what we're focusing on for that experiment. So we should just be clear at how we're defining it. A lot of them are pretty natural. Like if we're talking about making a basketball shot, usually your success would be making the shot, right? That kind of makes sense. But something like this, if we're researching identity theft and we're focusing on those who experience identity theft, we may call that a success. All right, so let's determine whether each experiment is a binomial experiment, and then if it is, we can specify the values for n, p, and q and list the possible values for x. And if it's not a binomial experiment, we're going to explain why. So let's do A over here. A certain surgical procedure has an 85% chance of success. A doctor performs a procedure on 8 patients, and the random variable represents the number of successful surgeries. So what we need to do is think about these 4 things to see if it actually fits the criteria. So first of all, is there a fixed number of trials? Yes, we're looking at 8 patients. So we do have a fixed number of trials of 8. Is each trial independent of the other trials? Yes, it is, right? So there is no reason why one person's surgery being a success or a failure should affect another person's surgery being a success or a failure. There are only 2 possible outcomes, right? Success, so the surgery goes well. Failure, the surgery does not go well. The probability of success is the same for each trial. Yes, we're told that it is 85% chance. We're not told that this changes from person to person. So overall, the surgery has an 85% chance of success. So yes, it is the same from trial to trial. And yes, the random variable counts the number of successful trials. That's how it's defined here. So all 4 criteria are met. So this is a binomial experiment. Now, in this case, n is going to be 8 because we're going to have 8 trials. So 8 patients are our trials here. P is your probability of success, and our chance of success is 85%, so 0.85. Now, Q is your probability of failure. So to find it, you just do 1 minus P. So 1 minus 0.85 is 0.15. So that's our probability of a failure. So there's still a 15% chance that this surgery is not successful. And what's the last thing we had to do? We have to list the possible values of X. So X, remember, is the number of successes we can have. So if I have 8 patients, you could have 0 successes. So all 8 surgeries fail. You could have 1 surgery be successful out of the 8. You could have 2 surgeries be successful, 3, 4, 5, 6, 7, or all 8 are successful. Now for the next one, we're looking at a jar that contains 5 red marbles, 9 blue marbles, and 6 green marbles. You're randomly going to select 3 marbles from the jar without replacement. So without replacement means that you take 1 marble out and you hold it in your hand. So you don't put it back in the jar. Then you take a second marble out. Again, you hold it in your hand. And then you take a third marble out and you hold it in your hand. So each time you take a marble out, you're not putting it back in. So the total number of marbles in the jar is decreasing. And then the random variable represents the number of red marbles. So red marbles is going to be our success here, right? So our goal is to pull red marbles. And we're doing this 3 times, right? So we're randomly selecting 3 marbles. So we'd have 3 trials here, and we want our success to be to get a red marble. So we start going through our checklist, right? Does the experiment have a fixed number of trials? It does. We're going to pull 3 marbles, so 3 trials. Is each trial independent of the other trials? Now, I want you to think here. This one's tricky, and the reason it's tricky is because it says without replacement. So if I take 1 marble out and I don't put it back in the jar, I have affected my chances of getting a red marble on the second try, right? Because I've changed the total and I've removed a marble. So these are not independent trials. They are dependent trials because I am not replacing that marble back in. I'm changing my total each time. I'm changing the dynamic of how many colors are in there. So these are dependent trials. So this does not qualify as a binomial experiment. So we do have to be just really careful about how we're reading these questions and defining them when we're going through our checklist. All right, so let's actually do some work. So let's say we do know that we actually have a binomial distribution. Let's keep moving forward. So there are several ways to find the probability of X successes in N trials in a binomial experiment. One way is to use a tree diagram and the multiplication rule. So if you're comfortable, you could do a whole tree diagram and figure it out that way using visuals. Another way, if you're more of a formula person or if it starts to get too complicated to do a tree diagram, is to use what's called the binomial probability formula. So in a binomial experiment, the probability of exactly X successes in N trials is given by this formula here. So it uses our combinations formula from last time. So this here is the same thing as this. We just kind of replaced it. And then you're multiplying it by your P, which is your probability of success to the X power, times your Q, which is the probability of failure to the N minus X power. And then we're multiplying this all out. So remember here, N is the number of trials. X is the number of successes in those number of trials. P is the probability of a success. and Q is the probability of a failure. All right, so let's actually go ahead and use this formula first and give it a try. So rotator cuff surgery has a 90% chance of success. The surgery is performed on 3 patients. Find the probability of the surgery being successful on exactly 2 patients. Okay, so first of all, we are kind of jumping in with the idea that we do have a binomial experiment here, but if you're not sure, you should go back and double check. So we do have a fixed number of trials. We're doing 3 trials. They are independent, right? So they're 3 different patients. They shouldn't be affecting each other on their rate of success. That probability of success is consistent. So we have that failure and success as our 2 outcomes, and the probability stays consistent throughout. And X represents the number of successes here. So it does meet all 4 criteria. So in this case here, our N is going to be 3, right? Because I have 3 different patients. Our X is 2 because I'm looking for exactly 2 successes. So X is the number of successes, so I want 2. Our P here is 90%, so 0.90, right? Because that's the probability of a success. And then our Q is 1 minus 0.90, which is 0.10. So let's go ahead and use this formula. So the probability of having 2 successes, and I'm actually just going to jump right over to this part right here, because everything is all nicely written out for me. Now our N is 3, so it's going to be 3 factorial over 3 minus, and then our X is 2, times, now P is 0.90, and again, X is 2, and then Q is 0.10, and then I'm looking at 3 for N and then 2 for X. So this is what my formula looks like. When I'm plugging in, I really just take my time. So I think you should take your time and define your parts first, then go to the formula and just plug them in. I wouldn't try to do it all at once. So I would take the time, define these first, and then plug them into my formula, just because it's a lot going on. So I have 3 factorial. Here, 3 minus 2 is 1. So 1 factorial times 2 factorial, 0.90 squared, and then 0.10 to the 3 minus 2 is 1. So 3 factorial is 3 times 2 times 1. 1 factorial is just 1, and 2 factorial is 2 times 1. Three times 2 times 1 is 6. Here I have just 2. And then again, just kind of simplifying with all time. Oops, sorry, this is a 1. I apologize. That was a 1. 0.10 to the first power is just 0.10. So now I probably want to just get my calculator out and finish the rest of this for me. So this obviously becomes 3. So 3 times, and then just be careful, make sure that 0.90 gets squared first before you're multiplying, using that order of operations here. And let's do it out. Get ready. So I have 3 times, so I'm going to put that 0.90 in parentheses, just so my calculator knows to make sure it does that first, times 0.10. And I get 0.243. And that's my answer. So my chance of having exactly 2 successes out of 3 is 0.243. So about 24.3% chance. Now, this is not 2 or more. So be careful. This is exactly 2 successes. So the reason this is probably so low is because the chance of surgery being a success is very high. It's at 90%. So my guess is that the chance of having all 3 being successful is actually a very large probability. So a low probability here doesn't necessarily mean that the whole experiment is a fail or anything like that. You want to keep in mind that this is for just 2 successes. So we could also find the probability for 0 successes, for 1 success, for 2, and for 3. So there's 4 different outcomes here, and we could do all 4 to get the full probability distribution. Now, another way to do it is to make a visual. So this one can get a little bit complicated, but what the tree diagram would look like would be this. So let's say we have our first surgery. Well, either you could have a success or you could have a failure, right? And then for the second surgery, so just kind of building off this, well, I could have a success or I could have a failure. And same thing here. I could have a success or I could have a failure. And then same thing for the third surgery, right? You could have a success or a failure in each of these cases. So what happens here? So let's look at the different outcomes. So my first surgery is a success, my second surgery is a success, my third surgery is a success. So that's this first group. Then I could have success, success, failure. Then I could have success, failure, success. Or I could have success, failure, failure. Okay, now let me do the next group. All right, so down here, I could have failure, success, success, failure, success, failure, 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 success, and failure, failure, failure. Just kind of squeezing that in there. Now, remember, we wanted to have exactly 2 successes. So this one, this one, this one, and that looks like it. So I have 3 possibilities there for getting, right, those 2 successes. So again, using my tree diagram, just to think about what could happen, right? So you could have 3 successes. Here you could have the first 2 are successful, the last is a failure. Here you could have 2 successful, but the middle one's a failure, right? So the different ordering actually matters here to keep those all in mind. So we have 3 different chances for this. Now, it is more complicated, so let's keep going. So if we think about probabilities, right, because I don't just want the number of outcomes, I want probabilities here. Well, the chance that the first one is a success is 0.90. The chance that the second surgery is a success is 0.90. And the chance that the third surgery is a failure is 0.10. And when I multiply these out, get my calculator out here, I get 0.081. And again, because these are independent events, then I probably shouldn't be affected along the line, so I can use those 0.9s and those 0.1s. And I'm going to do the same thing here, right? Probability of success is 0.90, probability of failure is 0.10, probability of success is 0.90, and I get that same result. And then finally here, probability of failure is 0.10, probability of success is 0.90. So again, these probabilities get multiplied because we have this and idea, right? Failure and then a success and then a success. And then finally, if I add up these 3 things, I have that same 0.243, right? So here we kind of are combining the idea of and or. So the probability of each of these individual outcomes occurring is 0.081. I'm using multiplication, so this and idea, but then I'm adding them all together at the end because this could happen, or this could happen, or this could happen. So I need to add up those 3 probabilities to get the total ways that 2 successes and 1 failure could occur here for the probability. So for me, if you're more visual, this works, right? I think this can be a little bit more complicated. I actually like the formula better here, as long as I can do my setup that I can plug in and simplify. But if you prefer to do a more visual way, that's okay too. Now, we can also do this on the calculator. So let me show you that as well. Okay. So we can do this on our calculator, and we're going to use the following steps. So you're going to hit the second button and then bars, and then we're going to select Binompdf. PDF, probability distribution. So I hit second, and then bars right here. And then if I look down towards the bottom here, or middle, you'll see Binompdf. Just be careful. Binomcdf is a different one. C stands for cumulative, so it's like an adding process. So we don't want this one, we want the PDF one. And then what you're going to enter are the following. I have it here. You're going to enter the values for n, then for p, and then for x. So my number of trials was 3. My probability of success was 0.9, and I'm looking for exactly 2 successes. I hit enter, and there's my 243. So I can do this on my calculator too, quite quickly if I want to. So as long as you can do the setup, right, that's the key here. Can you do the setup? Can you find the n, the x, the p, and the q? Then your calculator or the formula can do the rest of the work for you with calculating those probabilities if you like. If you like the visuals though, that's okay too. Now, just a couple other things to remember. Recall that when we have probabilities, a probability of 0.05 or less is considered unusual. So just kind of keep this in mind as you're answering questions. If any questions ask you about if a probability is unusual, then that 0.05 cutoff is what stands unless it says something different. So here our probability is 0.243. This is higher than 0.05. So this is not unusual. And then finally, and we'll get to this in a minute, by actually listing all possible values of x with their corresponding probabilities, we can actually do the full binomial probability distribution. So what we have here is just one of the outcomes, right? X equals 2, but there's actually 4 outcomes, x equals 0, 1, 2, or 3. So when we find the probabilities for all of them and make a nice table, now we have our distribution.